Okay, you know about gerrymandering. You know that politicians can draw some crazy-looking districts. But what is their end goal? Yes, they're divvying up voters to gain more seats for their party, but how many voters is too little, too much, or just right? This video looks into gerrymandering by looking into the partisan makeup of districts and how this influences their shapes. An effective tool for understanding and measuring gerrymanders is the weighted districts method, which uses dot plots to show redistricting plan imbalances and districts that just stick out funny. Along the way, the weighted districts method helps to understand the ultimate end goal of a gerrymander, the 60% district, which we will find is the most valuable district to have. To understand the weighted districts method, you don't need a math background or anything funky. All you need is a pen and paper to make a simple plot. A pen and paper may sound a bit old-fashioned, but plotting data points by hand really helps with getting a feel for the mechanics of a gerrymander. By the end of this video, with everything supplied to you but this pen and paper, you'll be able to make this exact dot plot of North Carolina's gerrymandered redistricting plan. And by creating a dot plot, you can determine the level of gerrymandering in any redistricting plan in the country. Not only will you be able to see which districts are the most valuable in evaluating a redistricting plan, you will be able to see how to fix these plans to turn them into fair plans. The weighted districts method includes newer concepts that allow for a more comprehensive take on evaluating and viewing redistricting plans. While this video is directed at the average user and educators who wish to teach gerrymandering and redistricting to their students, expert redistrictors can use it as an introduction to the weighted districts method. Now, what is gerrymandering? It's the manipulation of district boundaries to give one party more representation than they deserve. The result is an imbalance where one party gets something like 50% of the statewide vote share while receiving a much higher percentage of the state's legislative seats. While such an imbalance can highlight extreme gerrymanders, it's not useful when measuring a gerrymander or when correcting a gerrymander. Seats can be deceiving, as a seat is not a seat. For example, in this completely randomly drawn district, the red party won the last election with 82% of the votes. How would you rate this district? Is it beneficial or harmful to the red party? Some would say the district is packed with red voters, so that must be bad. But it has elected a red candidate, so isn't that good? On the other hand, down here, District 2 has also elected a red candidate, but with only 52% of the vote. How would you rate this district? District 2 is not packed, and it has elected a red candidate, but research has shown that district vote shares commonly vary by plus or minus 5 percentage points from election to election, and only occasionally will it shift upwards of 10 percentage points. Given these vote shifts, District 2 is bound to elect a blue candidate from time to time. So do we measure District 2 as a red district, a blue district, or something in between? A seat won with 82% of the votes is different than a seat won with 52% of the votes. Yes, each of these districts has elected a red candidate, but there's a lot more going on here. These districts expose the two forces encountered by redistrictors. That is, how packed a district is, and what is the probability of that district electing a candidate from a given party. Understanding the trade-offs between these forces is critical for redistrictors and those trying to understand gerrymanders. So let's put these thoughts into numbers and weight districts by vote share. To explain the weighted districts method, we start with a graph where each district is plotted in terms of its Republican vote share. So districts plotted on the right side of the graph are won by Republicans, as they have won more than half the votes, and districts on the left side are won by Democrats. Then each district is weighted between -50 and +50. Negative weights down here indicate the district is harmful to Republicans, thus beneficial to Democrats. And positive weights up here indicate the district is beneficial to Republicans and harmful to Democrats. In an election where, say, a Republican wins by a 60% to 40% margin, we call this a 60% district. As stated before, district vote shares shift from election to election due to candidate choices, as well as who is running for governor, president, etc. The weighted districts method accounts for this movement. Shifts of plus or minus 5 percentage points are expected, though shifts of more than 10 percentage points are far less common. Therefore, a district with a 60% vote share is almost certain to elect a Republican. Adding more Republican voters to this 60% district does not guarantee the seat anymore. Packing, on the other hand, is continual. Adding more Republican voters packs the district more and more and more, until it is harmful to Republicans. Therefore, packed districts way over here should be weighted negative. But where is that point when a district becomes so packed it is a liability? Is 70% packed? 80%? 90%? What does packed mean? Let's take a look at how the weighted districts method handles this. We know that a 50% district is not packed. In fact, a 50% district is just as likely to elect a Republican as it is a Democrat, benefiting neither party. Therefore, it gets a 0 weight. A 55% district will most of the time elect a Republican, so we weight it positively. The weighted districts method gives it a weight of plus 19. A 60% district is even more beneficial because it has a higher chance of electing a Republican, and it gets a weight of plus 25. The weights reach a maximum here because we are now 10 percentage points from 50%, and the district is all but guaranteed to elect a Republican. Increasing vote share past this point only packs the district more. The weight of a 65% district drops to 19. From there, weights steadily decline as districts become more packed. The 70% district has a weight of 10. The 75% district, the crossover point, gets a weight of 0. And 80% gets negative 10, and so on down the line until we get to the Republican district fully packed, 100% Republicans. That gets a weight of negative 50. The crossover point up here at 75% says, yes, Republicans get a guaranteed seat, but that guarantee is exactly offset by the harm caused by Republicans packed into the district. This is a very important concept. To one side of 75%, districts are harmful to Republicans, and to the other side, districts are beneficial. Where do you think this crossover point should be? Over here, we see that packing is not a static term, but incorporates a range. Then up here, the most valuable district for Republicans is the 60% district. There are enough Republican voters in the district to pretty much guarantee the seat. Yet the district is not yet packed. Because of this, gerrymanders aim for this 60% district. We have established our weighting function for all districts won by Republicans. The weights we plot here should resonate with how you value these districts. When teaching a class, encourage your students to come up with their own weighting function and weight elections using their own weights. Now, what about districts over here won by Democrats, as districts where Republicans have less than a 50% vote share? A 40% district is made up of 60% Democrats. Since a 60% Republican district has a plus 25 weight, this 60% Democratic district gets a negative 25 weight as it benefits Democrats to the same extent. And we can extend this line of thought with the rest of the dots, and the graph becomes symmetric around 50%. Again, below about a 40% Republican vote share, Democrats are guaranteed a seat. And vote shares past this point only pack more and more Democrats into the district, ultimately benefiting Republicans. And we have created the weighted districts method weighting function. Way down here are severely packed Republicans. Way up here are severely packed Democrats. Since districts are rarely way up here or way down here, the most beneficial Republican districts are here, and the most beneficial Democratic districts are here. In other words, when you're gerrymandering, you want your districts at one of these peaks and none of the opposition districts at the opposite peak. The equation used to create this weighting function is shown here. I'm only showing it for 30 seconds to explain it for those who wish to use it in Excel calculations, as it only puts into equation form what we have already learned. This equation is derived in the weighted districts method article linked in the video's description. The first term says that the more you pack voters into a district, the more harmful it is, and this is true all the way to 100% packed for either party. The second term says that adding more voters increases the chance of winning a seat, but only until about 60% vote share. This equation was used to plot the weighting function we see here. Again, we're not here to learn the equation, nor is it necessary for us to create a dot plot. A good equation, as this one does, reflects reality. It reflects what we intuitively know. You read articles stating, yay, this person won the election. Well, if that was a Republican, weight that district positive. If it was a Democrat, weight it negative. Then you hear, boo, this district is packed. If you agree with this, if it's a Republican district that's packed, weight it down here negative. And if it's a Democratic district packed, weight it up here positive because it benefits Republicans. Using this curve, this weighting function, you can use the vote share from any election in any district and find its weight by plotting it on the curve. That is, you find the district's value to the Republican Party. Plotting all elections from a redistricting plan allows one to view symmetry and imbalances in the plan. A fair plan, that is a well-balanced plan, will look balanced on this graph, having beneficial Republican districts and beneficial Democratic districts. A gerrymander appears lopsided as it has more weighting above the zero line, a Republican gerrymander, or below the zero line, a Democratic gerrymander. The weights given to districts right here near 50% show a key difference between the weighted districts method and other gerrymandering measures. A seat won with 49% of the vote is weighted similarly to a seat won with 51% of the vote. No matter which party wins the seat, the district remains weighted near zero. In contrast, comparing the number of seats won by Republicans or Democrats forces the district to be either Republican or Democrat, which not only throws a measurement off, the measurement jumps when the seat flips. This is one of several reasons the weighted districts method is the most accurate gerrymandering measure. It truly measures the value of a redistricting plan. As will be evident when we create the dot plot, the weighted districts method measures each individual district and shows its contribution to the entirety of the plan. It actually measures what gerrymanders are trying to do. That is, create the most valuable district, the 60% district for their party, and pack opposition districts. Then the plot shows you how to fix it as it points out districts that are just out there too far or just need to be adjusted. As a final note on the weighting function, we plot all districts according to Republican vote share. This is intentional as it is easier for Republicans to gerrymander than it is for Democrats, and here's why. This is a very basic map of North Carolina's political makeup. While this blue area up here is sparsely populated, half of North Carolina's population lives in these blue cities, where the centers are commonly greater than 90% Democrat. Because of this imbalance or asymmetry, even random redistricting plans tend to pack Democrats into districts. When gerrymandering, it becomes a simple task to pack even more Democrats into districts. Since these red areas out here are often less than 70% Democrat or so, packing Republicans into districts can be difficult, if not impossible. As a result, Republican gerrymanders tend to be cleaner and much easier to explain. This is why the weighted districts method uses Republican vote share on the dot plot x-axis. But to be clear, both parties gerrymander. This is not about Republicans or Democrats, as will be explained in the following example. Independent of which party creates it, a gerrymander hurts voters from both parties. So let's dig deeper into North Carolina and create a dot plot using North Carolina's U.S. congressional election results from 2012. The numbers used in this example are from Ballotpedia and are shown in this spreadsheet. North Carolina's 13 districts are listed in the first column. Each district's Republican vote share is listed in the second, and the third column is to be filled in later with the weight of each district. For expediency, I have already filled in this column. I like to order my districts by vote share from highest to lowest. Notice Republicans won the top 9 districts and Democrats won the bottom 4. The average of these district vote shares is the statewide vote share, and with a statewide vote share of 49% Republican, we see that in 2012 elections, North Carolina leaned just slightly to the left, though Republicans won 69% of the seats. We use these column 2 vote shares to create the dot plot. Starting at the top, District 3 has a Republican vote share of 63%, so we place the dot here. From that, we see that this district gets a weight of 22. So District 3 is very beneficial to Republicans. We entered 22 over here in column 3 of our spreadsheet. 60.9 gets a weight of 25. We're just guessing, we're coming close. 57.55, 57.4. These dots don't need to be exactly on the line, especially when they bunch up like this, but each dot must be properly placed above its vote share as accurately as possible. When determining the district weight to enter into column 3, yes, use the value it would be on the line, but you are creating a visual plot to show each district, to see each election. So create a piece of art with the data. That's what the dot plot is. It's a visual representation. 57.25, these districts are really bunching up here. Why would that be? Again, bunched. It's almost as if the Republicans who created this gerrymander knew that creating 60% districts would be the most valuable to their party, which is exactly what our weighting function tells us. 53.9. By the way, I use the term 60% district to refer to a district near the top of this curve. Near 60%. Now 53.05. Now on to seats won by Democrats. 49.9. There's a squeaker of an election. This one could have easily been won by a Republican. It can't be worth much. Gets a weight of -1. This is a good example of how the weighted districts method looks at the district, not the seat. We have a Democratic seat, but the district is not Democratic. It's neutral. Had a Republican barely won the district, the measurement would barely change. And that's the way it should be. See, 25.5. Now we're getting into the packed Democratic districts, 23.75. These districts benefit Republicans. And finally, 20.35 gets a weight of +9, and we put that weight way down here. And that's it. We have successfully created a dot plot of the 2012 U.S. congressional elections in North Carolina. We have weighted each district by how valuable it is to Republicans. Or, if we flip the graph upside down, we see how valuable each district is to Democrats. What does this tell us? Districts benefiting Democrats are given a negative weight down here. We see that no districts substantially benefit Democrats. We see packed Democratic districts, which benefit Republicans, and we see bunched Republican districts near the optimum vote shares at the top of our weighting function. A balanced plan has an equal weighting above and below 0. This plan does not. Simply looking at this dot plot, it looks like a gerrymander, because on average, the districts benefit Republicans. But Republicans getting more seats than they deserve or Democrats being packed is not the true harm of this gerrymander. The harsh reality of gerrymandering is there are few districts right here in the middle, near 50%. That means few close elections. That means voters don't choose their representatives in North Carolina, whether they're Democrat or Republican. Republicans up here will get elected barring any huge scandal. Democrats here will always get elected even with a scandal. In fact, Democratic incumbents in packed districts like these have voted for gerrymanders such as this, even though the gerrymanders are directed against their party. That's how they stay in business. That's how they keep their seat. Politicians will gerrymander when given the chance. It's all about me. When discussing gerrymandering reform, conversations that turn into an us versus them dialogue alienate voters on the other side, and such talk only hurts reform efforts. Since vote shares typically bounce around 5 percentage points or so, this graph shows that North Carolina voters will elect only 2 or 3 of their 13 representatives. The rest of the elections are all but guaranteed. That harms voters from both parties. Now, when you're looking for a gerrymander on these plots, or even if you're just looking at election results like we have in column 2, look for these 60% districts. Our spreadsheet shows 7 districts, all bunched around 60%. That in itself is suspicious. Articles talk about cracking and packing, yet they leave the concepts relatively vague. The true object of a gerrymander is not to pack your opponent, but to create a maximum number of these 60% districts. Packing is simply a mechanism, a means to achieve this goal. The weighting function clarifies the value of a 60% district. And remember, down here is also a 60% district, the most beneficial for Democrats. Looking at our dot plot, it looks like a gerrymander. But how is this measured? Here in column 3, we have the district weights. If the average of the weights W is greater than 5, it means the Republican seat share is more than 5 percentage points over what is fair and is considered a Republican gerrymander. Now be careful when I say seat share, because I'm treating it as the weighted districts method treats seat share, which is a more fluid concept. That's explained in the paper, but I won't go into that here. So when you're approximating, you can say like 5 to 7%. This plan gives an average weight of W equals 15.4, which indicates an extreme gerrymander. Again, this is evident just from looking at the dot plot. Let's look again here at this 49% district. Moving it to 51% changes the plan very little. Any measure of this plan should change very little. And this is true with the weighted districts method. The individual district weight changes little, therefore the overall measure, which is the average of the district weights, changes even less. When using seat share to measure this plan, the results become different as seat shares see the seat flip from 49% to 51%. Any measure using seat share also jumps, though the plan has hardly changed. Column 4 here uses the weighted districts method equation shown earlier to calculate the exact individual district weights. The average weight of W equals 15.7 indicates an extreme gerrymander. Scientists and redistrictors should use the equation when determining the validity of plans, though the equation is not necessary to understand gerrymander or the value of a redistricting plan. Eyeballing the weights like we did in column 3 gives us, the user, a much better feel for the values of the individual districts and how they influence the plan as a whole. If we're off by a bit eyeballing it, big deal. We still see and measure this as a gerrymander. The whole purpose of this exercise is to visualize a gerrymander. You don't need an equation. You just need to download this weighting function and plot the dots yourself. Easy peasy. The final number, W equals 15, quantizes the gerrymander, but the entirety of this graph helps explain the role each district plays and which districts need to be adjusted to get a fair plan. Okay, now that we know these 60% districts are behind the goal of a gerrymander, let's take a look at the theory behind the creation of these 60% districts. Say we have this 50-50 state. It has 4 districts. Each district has a weight of 0. So the overall weight of the plan is 0. With all districts at 50%, the statewide vote share is also 50%. Ignore the color of these dots for the moment, as they benefit neither party and they're all at 50% vote share. Now, creating a 40% district gives Democrats a dependable seat. To keep the state balanced, we create a 60% district, which gives Republicans a dependable seat. Notice that the plan still looks balanced. The overall weight of this plan, that is the average of the district weights, is still W equals 0, and the statewide vote share is still 50%. Along the same lines, creating a 30% district allows us to create a 70% district, and this gives another nicely balanced plan. But we're gerrymandering. We don't want a balanced plan. Creating a second 60% district keeps the statewide vote share at 50% and benefits Republicans with another dependable seat. Finally, creating one 20% district allows us to create 3 60% districts. We still have a 50-50 state, yet Democrats get 1 packed district and Republicans get 3 fairly reliable seats. In other words, we started with all 4 districts at 50%. We have moved 1 district a total of 30 points to the left and 3 districts a total of 30 points to the right. This shows why packed districts are so effective to the opposition party. The weighted districts method weights this plan at W equals 21, an extreme gerrymander. Again, we started with 4 close elections. We ended up with 0 close elections. Voters do not choose their representatives. In the North Carolina plan up here, since North Carolina is about a 50-50 state, we should see a cluster of districts around 50%, but we don't. Instead, these 3 packed districts gave Republicans this cluster of dependable seats. That's how the magic is done. Now, how does this dot plot compare to reality? That is, how does it relate to the actual political makeup of North Carolina? Remember where the cores of these blue areas can be 90% or more Democrat, and half the state's population is within these cities? If we can put a majority of these blue areas into a small number of select districts, we will have packed districts. And here are North Carolina's 3 packed districts: NC01, NC04, and the infamous NC12. By gutting the center of the cities, they put a good portion of the state's Democrats in these 3 districts. I know what you're thinking. You're thinking they got NC hammered. Can't touch this. And you're right. Now Democrats can't touch this or break it down. NC started as a 49% state, and packing a good portion of NC Democrats into these 3 districts left the remainder of the state 57% Republican. And it's a relatively simple task to crack that remainder into these districts up here that center around 57%. Understanding how this map translates to this plot is crucial, not only in understanding how a gerrymander works, but understanding these methods are imperative when creating fair plans or correcting plans that are even just a bit off. The weighted districts method not only measures a redistricting plan, it helps you understand it. A fair plan is an equally balanced plan. This plan is not. A fair plan has W close to 0. This plan does not. The dot plot shows imbalances in the plan, and we can see what needs to be fixed. Moving the bunch districts at 60%, kind of close to 50, over to 50%, and then moving the pack districts way in will create a much more balanced plan. And that's what fair redistrictors aim for. A fair plan with the average of the weights close to 0. And now I'd like to hear from you. Hopefully you've come to understand the weighted districts method and the dot plot. Feel free to post a comment below or a question. And more importantly, post your dot plots either here or on my Twitter feed. The more information that gets out there, the better. If you care to learn more, download the article linked in the description below this video. It further describes the theory behind the weighting function. To use the weighted districts method and plot your own data, take a screenshot of the weighting function or create one in Excel using the equation provided. And don't forget about those 60% districts.